Hello everybody, and welcome to the first of a few Physics 2 online lab simulations. Since we've moved to a solely computer-based model for the rest of the semester, I thought it might be helpful to have these videos as a backup in case people were having difficulties getting these labs to run on their computers, or any such thing like that. So, before we jump in, please ensure that you have read through the lab manual already. I'm going to be going through a little bit of it, but it would be very good for you to have already done a bit of research on your own. Just read through the lab manual. And a couple notes on that. This lab manual was adapted from the original experiment that we were going to be doing. So there are some things that will not be relevant to the online lab that we will be performing today. I will point those things out as we go, though. So, jumping right in, the goal of this law is to observe the effect of a bar magnet and an electromagnet on a conducting loop of wire. Now, as we know, or as we'll find out, when you take a bar magnet, such as this one, and you throw it through a conducting loop of wire, a current will be induced on that loop based on the movement of this bar magnet. And we will get into that in a second. First off, there are a couple things we need to know about. First thing is this little device here. This device is known as a galvanometer. Now, a galvanometer is a device that measures small fluctuations in current within a wire. You don't need to know much more than that, other than the fact that if it notices a small change in current negatively, it'll deflect to the negative direction, and then if it notices a small flux of change of current in the positive direction, it'll deflect positive. It's a pretty, what should I say? It's a pretty qualitative device in the sense that it just gives you an idea of what's going on, as opposed to an exact measure of what's going on. So there's that. Secondly, a solenoid, which is this device here or this device here, is just a coil of wire. That's all it really is. This experiment will be using two solenoids, and basically this smaller one here, or the smaller one here, and this bigger one here. And I will explain a little bit why in a minute. There is no power source for this simulation because we don't need one, and I'll explain why. Finally, we've got this little light bulb here. That's just, again, another qualitative measure of the current running through a wire. You can imagine if there's not a lot of current running through the wire, it'll be kind of dim. If there's a lot of current running through the wire, it'll be pretty bright. So in any case, that is pretty much all of the equipment you need to know for this lab. As far as the theory goes, let's talk about the magnitude of a magnetic field within a solenoid. And that is given by this equation here that I've just highlighted. B is equal to, or about equal to, mu times n times I. Okay, let's walk through those variables for a second. The magnetic field is obviously denoted by B. Mu is just the permeability of the space that you were using. Let's assume that, for now, that it's mu naught, which is the permeability of free space. N is the number of loops in a wire, or in the solenoid, and I is the current that is running through the solenoid. Now, you might ask yourself, how do we figure out the current? Well, first of all, we need to figure out the magnetic flux through a certain area. The magnetic flux, denoted by the Greek symbol phi, is the magnetic field times the area of the cross section times the angle that it's changing at. Now, according to Faraday's law, which is right here, a changing magnetic field that crosses through an area of n loops of a conductor induces an EMF that the conductor can create a current. We all know that an EMF is essentially the same thing, up to a couple other variables like resistance, is essentially the same thing as a current itself. So what this tells us is that basically the voltage through a current is going to be equal to the negative change in flux of the magnetic field over time. So this should give you an idea that if you have a magnetic field that is changing in time, that will induce a current on a loop of wire. And we will be simulating that today by means of these wonderful Colorado lab simulations. So let's jump right into it. I'm not going to be answering all the questions as they come up in the lab manual. Those are for you to answer so that you can have a little bit more understanding of what's going on. Hopefully, as I'm explaining things and as we're going through things, though, you will get an idea of how to answer those questions. Always feel free to email me or go to the physics help room online, not in person, for help if you are having trouble answering these questions. So, let's jump right in. Step 1 says to insert the bar magnet slowly into each of the solenoids or coils of wire, both of these two, okay, and then remove it. And then it asks you 2 questions. Does the sign change or remain constant when you remove the magnet as opposed to inserting it? And then which coil gives you a higher voltage reading? So try to think of how to answer those questions as we're going through this part. So you can see I've got my magnet here. I can drag it into this coil of wire, which I will do now, and then take a look at what happens to the galvanometer as I do that. So inserting it, you can see it deflects negative a little bit, and taking it out, you can see it deflects positive a little bit, and then we get a burst of current through this light bulb here. Okay, so that's for this one. Now let's go through the bigger one here. Now take a second to think about what you would expect to happen based on this equation here. You know that the magnetic field is proportional to the number of loops in the wire. So if you have a bigger magnetic field within the solenoid, then you might expect that you'd get a bigger current. So let's see what happens here. As I insert it in, you can see it deflects fairly substantially to the negative direction, and as I pull it out, you can see it deflects fairly substantially to the positive direction. And again, we get a nice burst of light from the light bulb there. Alright, hopefully that gives you an idea of how to answer some of the questions for number 1. Let's move on to number 2. Number 2 says to insert the magnet more quickly into a coil of your choice. What happens about the measured voltage from your earlier measurement? Alright, now again, this is just going to be qualitative. You're really just going to be looking as to whether or not what you measure is higher or lower than before in deflection magnitude on the galvanometer. Alright, so as I take this magnet here and I insert it, I'll do it slowly first so that you can get an idea for what to look out for. So moving kind of slowly, you can see it deflects negatively and then deflects positively. Now if I go faster, you can see it deflects more to the negative direction, and then if I pull it out faster, it deflects more to the positive direction. Let's do the same thing in the bigger wire here, or in the bigger loop of current. So moving slowly, you can see it deflects, pretty well to the left, and moving slowly, you can see it deflects pretty well to the right. Now if I move quickly, it deflects all the way maximally to the left here, and the light lights up a lot. And if I do the opposite happens. Let's just show you that one more time. Slowly, we get a bit of deflection to the left. Slowly, we get a bit of deflection to the right, and then quickly, we get the same thing, just kind of amplified. Great. Okay, so moving on to number 3. Note the sign of the voltage when you're inserting the positive end of the magnet into the solenoid. Okay, so this is the positive end, or the north end of the magnet. As I insert it into the solenoid, the deflection is negative, and as I pull it out, the deflection is positive. Now it says to use the button at the bottom of the simulation to rotate the magnet. Great, so now I've rotated the magnet, you've got the south end where the north end was before. And insert the south end of the magnet. And then it asks you the question, does the voltage match your measurement of the north end? Okay, so putting it in, we have a positive deflection here, and pulling it out, we have a negative deflection. Whereas before, we had a negative deflection putting it in, and a positive deflection pulling it out. Now I'm going to try to do this at about the same speed so that you can see what's happening here. Okay, good. Now you can see I went about the same velocity inserting it as I did pulling it out, and we had about the same magnitude of deflection in the negative and positive directions. Now if I do the same thing here, you can see it deflected to the right just about as much as the negative, or just about as much as the positive side did pulling it out. Now, if I pull the magnet out, you can see it deflects to the left, and about the same magnitude as it does when I slowly insert the magnet in from the north end. So hopefully that gives you an idea of how to answer the questions for number 3. Alright, moving on to part 2 of the lab. This is the Java portion of the experiment. We've got item 4 says to download and running the program, which I've done, and to select the 4th tab at the top of the user interface called Transformer, which we have done here. Now it says to, on the right side of the window, select the alternating current, which I have done for the current source, and the voltage meter for your indicator. So this is my indicator here. You can either have a light bulb or a voltage meter, but this is a bit more quantitative, which we're going to use that. And it says to set the AC current supplied to 50% for both frequency and amplitude. Alright, so I can adjust the frequency of the alternating current here, and I can adjust the amplitude of the alternating current here. So we're going to set each to 50%, if I can get it to line up here. Let me just reduce the sensitivity of my mouse. Alright, and 50%, great. Do the same thing here. Awesome. Now it says to move the current supply and coil to the following positions, as far as possible from the pickup coil. Okay, so this is going to be the pickup coil. So we're going to move this as far as possible away. Oh, sorry there. As far as possible from the pickup coil. Now, as you can see, these little dots on these wires represent the electrons, and so you can imagine here, this coil of wire is about as far away as possible from this coil of wire, given the setup that we have here. Okay, now it says to compare the maximum voltage indicated in all three positions. So we're going to take a look at what happens to our galvanometer here when we start up the current source. So starting at the current source, you can see there's a magnetic field indicator here. If it's brighter and more solid, that means that it's a stronger magnetic field, and as you go further away, you'd expect it to die off. And as you can see by the fact that it gets dimmer and dimmer over here to the point where you can't really even see it, you can see that that is kind of what's happening here. So this alternating current, you can see that these electrons are kind of wiggling in the wires, moving back and forth, which is what's causing this alternating magnetic field. Given what we know about magnetic fields and EMFs, this is a changing magnetic field with time. So because you have this current kind of going back and forth, back and forth, back and forth. So if this coil of wire connected to the galvanometer here is subject to a strong enough magnetic field, it should cause these electrons to wiggle, okay? But as you can see, when they're sufficiently far apart, nothing really happens because they're effectively infinitely far apart, given this setup. So I'm going to pause the simulation real quick. And it says to move the current supply and coil to be adjacent to themselves now. So I'm just going to do that here. And you can see now they're next to each other. And when I hit play, what I would expect to happen is that, these electrons are going to wiggle because we have a current supply here, but then you'll probably also see these electrons start to wiggle and the voltage meter move back and forth a little bit as well. So let's see what happens. Okay, cool. So we kind of see that what I said is coming to fruition here. This little voltage meter is kind of ticking back and forth, very, 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 very lightly though. Now, if I pause the simulation once again, it says to move the pickup and coil and the other coil inside each other. So now we've done that, and we're going to take a look at what happens to the galvanometer in this situation. So you can see the galvanometer starts deflecting to the left and right, a bit more than it was before. And that should make sense because the closer you are to the source of the magnetic field, as you can see visually here, the stronger the magnetic field is. So that would mean that the stronger the EMF is, and therefore the stronger, or the higher the induced current in this wire here. So let's just show you all these situations again. I won't pause the simulations this time. And you can see the electrons are still wiggling in here. But over here, because they're sufficiently far apart, we don't really get any movement in the galvanometer. Now if I move them closer to each other again, you can see the galvanometer starts kind of going back and forth, which means that there's some kind of current running through these wires. And if I put this one inside the other one, it starts to wiggle back and forth even more. And I'll just do that one more time, except this time I'm going to amplify the current in the wire, or going to amplify the power output so that you can see a little bit more deflection in the galvanometer. So over here you can see it's not really deflecting as much at all as before. Now if I move them close to each other, now it's deflecting a little bit like it was before. And if I move them directly on top of each other, you can see it's actually deflecting quite a lot. Okay, so I'm going to pause the simulation there. And one quick note that I forgot to mention before. If the little tick marks on this, you can subdivide those however you would like, though I would recommend calling the middle 0. That's kind of the only hard and fast rule. Call the middle 0. And then the first big tick to the negative side, I would call about 1 volt. And the first negative 1 volt. And then the first big tick to the right side, I would call about positive 1 volt. So you can see here that if this, between two ticks, there's 1, 2, 3, 4, or there's 1, 2, 3 little smaller tick marks. So each of those are going to be about, a third of a volt. Just as a point of fact there. So as finally, it says number 8, point 8 here says, with the current coil still inside the pickup coil, so we're going to move it here, adjust the frequency to 5%, and then 25%, and then 100%, and note the change in the maximum voltage between these frequencies. Okay, so let's go ahead and do that. I'm going to reduce the amplitude to 75% here, just so that you can get, just so that you have a pretty good idea of what's going on. Now, let's think about what we would expect to happen real quick. So if we're reducing the frequency here, what's happening is that the electrons are moving, and then kind of stopping and shifting directions, okay? Now, if I increase the frequency, the electrons are just going to start, again, wiggling back and forth like they were before, but more quickly. And if I increase it to 100%, they're just kind of moving back and forth very erratically, okay? So take a look at what happens to the magnetic field around the solenoid while that's happening. It's relatively constant until they stop and change directions, right? So it's constant, and now we're changing, okay? So given what happens, now if I increase it to 100% here, you can see the magnetic field is just flipping sign and kind of changing direction over and over and over again very quickly. So go ahead and think to yourself what might happen given those two situations in another coil of wire. I'll give you like 5 seconds to think about that. Okay, so let's actually see what happens. I'm going to pause the simulation. I'm going to put the two wires in overlapping each other, and take a look at what happens to this meter when I turn it on. And I'll let it go through a couple cycles here. So as you can see, nothing is really happening to the galvanometer at 5% frequency. And that's because, as you can see just by kind of the electric field or the magnetic field representation here, it's relatively stable throughout this entire process. Now, if I adjust the frequency to 25% after I pause it here, what we should expect to see is that this galvanometer starts to deflect a bit more than it did before. Let's see what happens. And that's because the magnetic field is going to be changing a bunch more than it was before. Okay, so as you can see, now the magnetic field is shifting at about 5 times the rate it was before, and we're getting a lot more deflection in the galvanometer than we were before. Alright, now let's move on to changing it to 100%. Again, I'm going to pause the simulation here and move this up to 100%. Now, given the fact that the magnetic field that we saw earlier when I set it to 100% was just kind of going back and forth very erratically, we should see a pretty big change in this galvanometer. Let's see what happens. Alright, cool. And as you can see, we're kind of oscillating between -1 and +1 volt here, just going back and forth, back and forth, back and forth. And the deflection was much greater than it was at 25%. And just to kind of go through this again so that you can see it again, I'm going to set it back to 5%. And you can see we don't really get any deflection, or if there is any deflection in the galvanometer, it's effectively unnoticeable. Now, if I drag it up to 25%, you can see we start getting some deflection in the galvanometer. It's kind of going back and forth, oscillating between maybe 1/3 of a volt and -1/3 volts. And if I bring it up to 100, it's just oscillating back and forth between -1 and +1 volts over and over and over and over again. Cool. So hopefully this video has given you the opportunity to take the data that you need. Again, just make sure that you fill in all of this here. Here you're just noting the deflections of the magnets in the previous section, and here you're noting the magnitude and direction of, the magnitude and the sign, so positive, negative, of the voltage from the transformer that I just did here in each of these situations. So go ahead and do that, and make sure that you do your analysis and all of your discussion questions and whatnot in your lab report, and we will be all good to go. If you have any questions, feel free to email me. All right, and thanks for joining. Appreciate it.